Here in the painted wetland, the reeds and lily pads suggest a natural coordinate grid. Our guide, the wise Math Shiba, sits among them to observe the patterns of the marsh. In this environment, two separate mathematical rules can operate at the same time, generating two distinct trails of numbers. But looking at those numerical trails in isolation doesn't show how they interact or influence one another. To understand the relationship between these independent patterns, we need a way to connect them visually. Wren, the great blue heron, begins her journey at a single, unified starting position on the muddy bank, 0. She creates two paths simultaneously. One trail moves in steps of 3, while the other moves in steps of 6. Mapping these stops onto a unified grid displays the mathematical connection between the two paths. This translation process turns abstract stepping rules into a definitive visual proof. First, we isolate the data. Rule A is add 3 from 0, which generates the sequence 0, 3, 6, 9, and 12. Rule B is add 6 from 0. This faster path generates the terms 0, 6, 12, 18, and 24. Each subsequent number in these lists is calculated simply by adding the fixed rule amount to the term before it. While these lists are predictable, they remain mathematically isolated as long as they stay in this linear format. To connect them, we pair the lists by their corresponding positions, matching the first term with the first and the second with the second. We format these aligned terms into ordered pairs, 0, 0, 3, 6, 6, 12, 9, 18, and 12, 24. These corresponding terms from our lists are now the x and y coordinates of a single spatial point. Ordered pairs are the structural link that carries linear arithmetic data directly into two-dimensional geometry. Now, Wren the heron can project that numerical data into precise spatial coordinates within the painted wetland environment. We plot the first 3 pairs on the coordinate grid. Lily pads appear at 3, 6, 6, 12, and 9, 18. These separate coordinates form a perfectly straight path across the marsh. The act of plotting gives a physical shape to the mathematical relationship. By comparing the B coordinates against the A coordinates, we can see a consistent multiplier in the distance. The spacing shows the math in action. Because Rule B adds 6, exactly double the 3 added by Rule A, every B term is twice its matching A term. 6 is twice 3, and 12 is twice 6. To find any relationship, build each pattern from its rule, pair the corresponding terms, plot the points, and then interpret the graph. If the rules change to add 2 from 0 and add 4 from 0, what would the first 3 ordered pairs look like, and how would B relate to A?